The last part of complex numbers, and frankly probably the hardest part of complex numbers, is adding two periodic functions together to get a third periodic function. So you can see that I'm going to add sine x and 2 sine x plus pi by 2 and get another trig equation together. And it's not as simple as just like looking at the numbers and getting that, for example. It doesn't work quite like that. The easiest way to do it is to convert it into complex numbers and then take it back out again. And to do that, use the general formula e to the ix is cos x plus I sine x, which we know from the Argand diagram anyway, because the cos x is the x part and sine x is going to be the height. Now, what's important to note is that cos obviously is the real part and sine is the imaginary part, because obviously sine has the I there and cos does not. So if you're looking at sine, you've got to be thinking about imaginary parts. If you're looking at cos, you're looking at the real parts. So I'm going to write that down. Sine is the imaginary, cos is the real parts. So if you think about sine x is the imaginary part of e to the ix, right? It's just here, it's this bit. So the imaginary part of e to the ix is sine x. Exactly the same logic for the next bit. 2 sine x plus pi by 2 is the imaginary part of 2 e to the I x plus pi by 2. It's literally just copying and pasting, basically. Now, if I expand the brackets up here, I get the imaginary part of e to the ix, and I have 2e to the ix plus I pi by 2. Which, if you think about it, you can get rid of that little plus and just put an e there. Remember, when you multiply with powers, you add them effectively. So you'll notice that I have an e to the ix and another e to the ix. So therefore, if I take e to the ix outside the brackets, and this is always the way to do it, get 1 plus 2 e to the I pi by 2. From here, you can use numworks. If you just put this into numworks, which I'll do now, you will get a complex number. So let's put it in. 1 plus 2 e to the I pi by 2. So it's given us 1 plus 2i, which is helpful, but we want it in Euler form. So to change it, what I would do is I'll go to settings, and I'll come down to complex format, and I'll change it into polar. You can put it in Cartesian, or you can put it in polar. Let's put it in polar, and let's go back, and let's do the same thing. So I'm literally just going to copy and paste this in. And this is the answer we want here. So I get 2.24 e to the 1.11, and there is an I on the end there as well, as you can see. Oops, sorry, it's right there. 2.24 e to the 1.11 I. So that's just changing that bit. So I've got imaginary e to the ix. What was it? It was 2.24 e to the 1.11 I. I haven't done anything. All I've done is I've put this here into numworks and I've changed it. So at this stage now you can combine it back together again. I get 2.24 e to the 1.11 I e to the ix. It's just multiplying it out, which is obviously the imaginary part of 2.24 e to the I x plus 1 point, if I can get rid of that, 1. And that's it. Now, you've got to remember again, and right at the beginning, we said sine was the imaginary part. So if I'm taking the imaginary part of this, I'm going to be left with just the sine, because it's just the imaginary part of 2.24 cos x plus 1.11 plus I sine x plus 1.11. But because I'm only taking the imaginary part, that's what the IM stands for, I just get 2.24 sine x plus 1.11. So this part is the real, with the cos, obviously, that's the real. The imaginary part is this times that. And so that's your answer. And that would be how you add them together. I'll do it again with just the real parts with cos. Okay? So, and I'll do this quite quickly. You can follow exactly the same logic through. Let's do the same question, but let's now say it was cos 2 cos x plus pi by 2. It's the same sort of question, but now we're doing with cos. Okay? So cos is the real part, so I take the real part of cos being e to the ix, 2e to the I, x plus pi by 2. So I'm taking the real part and I'm going to factorize e to the ix. This is exactly the same as before. There is literally no difference at all. The numbers may change, but everything else is the same. I put this into numworks, and I'm left with the real of e to the ix, 2.24 e to the 1.11 I. Cos is the real, so I get exactly the same thing as before. I get 2.24 cos x plus 1.11. And so you can see, obviously, if it's cos here, it's going to be cos at the end. If it's sine, it's going to be sine at the end. The same logic follows every single time.